Hello, folks. How are you? How are you doing? I hope you are doing well. This is Saddam Leonardo Cap, and welcome back to my another video in which this is lecture 2, and I'm going to talk about vectors. So let's get started. In this video, I'm going to first tell you about the basics of vectors. Then I'm going to show you that if any quantity is a vector, what are the properties that it has to follow. And then I'm going to talk about the dot product. And in the lecture 3, I'm going to talk about the cross product because it involves a lot of matrices and all these things. Now, it may seem to you that vectors is going to be a very basic thing, but I am going to discuss a more important thing is called n tuples. Let us say that suppose you have a vector, then how it going to look like for in n dimensional space. So this is going to be a very interesting one. So let's get started. So when I'm going to start with vector, first of all, I'm going to describe that how we are going to represent vector. Any vector is represented by, let us say, quantity A is represented by A. Otherwise, some people prefer to write it in a bold letter, which is A. So both the quantities are basically showing the vector quantity, right? So if any quantity is a vector, that we are understanding that it has certain kind of magnitude and there is a direction. So vector has some quantity which has certain magnitude. It is 5 centimeter, 3 centimeter, 6 centimeter, in which direction we are talking about. So a vector is always contain this information, magnitude as well as direction. So anything which is represented by some kind of an arrow is called vector. Now, one of the interesting things that is coming with the vector is that a vector, let us say I have one vector A, and then there is another vector which is your B vector, then the C vector would be like this. So basically this is, we are going to be a tail and the arrow is called head. So the vector is going from tail to head and again tail to head, and then the resultant vector would going to go to this head. So how are we going to write this triangle law? The triangle law is written as we are starting this our journey from here to here, then from here to here, then I can just reach there by using just C. So I can just write it as A vector plus B vector is basically going to C vector. All right. Now, similarly, I can show you a more interesting thing. Let us say one vector is another side, another vector is over side. Let us say this is A vector, B vector. So what could be the C vector? So I can just write it down. If somebody has given you this way, I can simply simplify it because we have certain vector and certain direction, but I can always multiply with negative number and change its direction. So this vector would be minus A vector. This vector is already B vector, so I can simply go over here. So I have minus A vector, then I'm going to B vector, and then I have C vector. So in this case, our C vector is basically B vector minus A vector. So by multiplying any vector with a negative number can be changed, our direction can be changed. Understood? Now similarly, a vector over here is like this. Let us say A vector, another vector is over here, B vector. Then where could be the resultant vector or C vector? The C vector would be somewhere near this one. This would be C vector. How we know? We can just say that, okay, I can take one of vector which is parallel to B from here to here, and another vector is parallel to this guy over here, or let us say this one. So this has now becoming, oh, sorry about it. So this is like this. So one vector is going to be parallel to B vector, and another vector from here to here is parallel to A vector. So again, use the triangles law. From here I can go from here to here, and again I am coming back to this one. So OC is equal to OA plus AB vector. So this is your A vector and this is your B vector, and then I have having C vector. All right. Now this is again two vectors, addition of two vectors. So there are some properties of this addition. Let us say I have A vector plus B vector. I can always write it in this way, B vector plus A vector. All right. Now if I am multiplying with some negative number, let us say a vector is multiplying with some kind of constant, there will be no change in the direction, everything would be fine, where C is a non-zero real quantity. All right. On the other hand, if, and this is also positive, on the other hand, if I'm multiplying anything by some negative quantity, then obviously it will, the vector will, the direction will be not same, it will going to be changed. So that's why I cannot just write that A minus B vector would be same as B minus A vector. This is going to be wrong. in the vector quantities. So whenever we are doing some stuff with vectors, then we have to always be care that are we doing addition or subtraction. So in addition things are very good, but in subtraction things we have to care about at whose magnitude is greater and so on. So vector can change the direction. Another very important aspect I'm going to say that, let us say I have three vectors, a vector, b vector and c vector. So if I am doing the addition, first I'm going to take the addition of this one, and then I'm going to take the addition with another one. It There would be no effect if I am just leaving this vector aside and then first doing the operation for b vector plus c vector and then adding a vector. So nothing would be changed. So this is called again the distributive law and so forth and so on. So if any quantity is following this commutative relationship, distributive relationship, then you can just say that it is going to be a vector quantity. Now most important part with the vectors is that we can have different kind of coordinate system. For an example, I had shown you that we can be Eulerian coordinate system. Maybe you have in Euclidean coordinate system. You can have n-dimensional coordinate system, maybe 4 dimension, 5 dimension, 6 dimension. Or maybe your space is non-Euclidean, means that the space has some kind of curve. The vector is not a vector in one coordinate system is going to be vector in another coordinate system. The vector won't change. What it can change is that of some magnitude. We can call it as a coordinate of the vectors. All right. So magnitude can change, but a vector, the quantity itself won't change. So a vector is vector irrespective of which coordinate system you're talking about. So that's why these properties are just there. All right. So in whenever you will do the general relativity, this will come out as you can construct some quantities. Those quantities will be vector quantities. For example, as electric field, magnetic field, these are vector quantities. So they are going to remain a vector quantity either you are in curved space or you are in some flat space. All right. So I am just using some technical word which I shouldn't use, but never mind. Now for example, I have some coordinate system, let us say over here y and z, and let us say we are in 3D coordinate system x, y, z. Consider I have some kind of position vector or some point I have to locate it. So obviously it is going to have some position vector from the origin. All right. So this position vector, let us say the coordinate would be x, y and z. So I can just write down x hat, y hat and z hat. What does it actually represent? It represents something in x direction, something in y direction and something in z direction. All right. You may have heard this one, that x I hat, y j hat and z k hat. All right. So this is also true. Now in some sense we can also write it as x e1 e1 hat or e1 for the unit vector, y e2 and z e3. We will also see that for unit vectors these are called I hat or x hat or e1 e2 e3, they are called the unit vectors. All right. So this is we can also write it down. Now you can also think of it that we can also write it in terms of matrices. How? Let us say I have x, which is basically showing you that x component of the position vector. I can write e1 as 1 comma 0 comma 0. Similarly y, I can write 0 1 comma 0 and z 0 0 comma 1. So what basically it will give you some matrices, because when you are multiplying with x over here, it's 0 it's 0, so the whole quantities will be 0. Similarly I'm going to multiply over here x 0, y is basically 1, similarly z 0, and this quantities would be z. So this r vector is basically a part of a matrices. You can also think of it as a matrices. So now this is basically 3 cross 3 matrices. So these 1 0 0 0 1 0 0 0 1, they are called unit vectors. All right. So now since we are in 3 dimension, that's why you are seeing that is called 103 components. All right. Otherwise for n dimensions we have n coordinates. So these are called unit vectors or the basis vector. All right. And these basis vectors are extremely important. In so many cases we are going to look for these unit vectors. We are not worried about that what happens to the coordinate system. All right, because these x y z, they are just the coordinates. How these vectors are going to change, it's our real task. So mind it that unit vectors can be represented as x hat, y hat and z hat. or I cap, j cap, k cap, or e1, e2, e3. These are called unit vectors or the basis vectors. All right. So that is the very crucial thing that you have to understand. So this is one thing. Another important thing is, let us consider that I am in two dimension x and y, and let's say that I have some vector considered to be a vector. Now we can take a projection of any vector in any dimension. Projection of a vector in any basis, or any vector. Consider that I have x and y. We are in x and y coordinate system, so it can be represented x hat and y hat. All right. So any vector can make is making an angle theta with this one, with x hat. All right. So I can always find out the projection of this vector around x hat. So when we say that projection of a on x hat, so what does it, how we can find it? We can just find it, the projection of a on x, by just taking that. Okay, we can just take a perpendicular distance from here. It would be parallel to y hat. So I can consider cos theta is going to be magnitude of a vector. All right, cos theta is, sorry, something like this. Let us say this is ax, so this is your ax quantity, and in the length of this vector would be this guy. All right, so I can simply write ax would be this a cos theta, right? So if I have to find out that what would be the projection of, I can just write projection of a vector on x hat would be, just simply I can write a vector is equal to magnitude of a times x hat, or you can just say that a vector dot x hat. All right. So I can simply say that you can just projection of a on x is going to be just what you can say is a real quantity, so it cannot be a vector. So ax, I can label it ax is equal to a vector dot x, and we have to use the dot vector concept. So I hope that you understand few of things. So magnitude of a, magnitude of x hat, and then the angle between them. So actually ax is basically parallel to x hat, therefore that angle would become theta, obviously 0 degree. So a thing is that what we are actually calling it, that magnitude of a could, what could any the magnitude of a vector would be anything. Now x hat, the magnitude of unit vector is always going to be 1, and then there is something called cos theta. All right, so this ax would be a cos theta, or from here, from the geometric way, we can easily find out. All right, so you can find the projection of anything on any vector. So when we are talking about projection, then it means that it is making an angle theta with respect to that one. All right, so consider that you have u and there is some kind of vector v, and let us say making an angle theta. So you can just say that, okay, what would be the projection of u onto v? So I can just simply say that u cos theta and v hat. All right, so this is all be going to be u vector, and then this is going to be v vector. It might not be possible that for arbitrary vector this v hat is going to be 1, but for x hat it's always going to be 1. So in this way we can take a projection of any vector onto another vector. All right, so this is again a most important part. Now and because of this projection we can have components. Let us say I am drawing a vector in x and y, and people can estimate what would be the components of this vector onto x and y. So when we are talking about breaking the components, then we have to just make an angle with respect to any axis, particularly prefer to be x axis, and then we can just take a perpendicular line which is going to be parallel to y hat. All right, so the components means that the x coordinate and y coordinate of some vector. So you can use cos theta to be just write down ax I'm going to write as magnitude. And similarly over here, if I want to find this one, then I can use sine theta is going to be, I can just say that this is ay ay and then magnitude. So ax of this vector would be magnitude of a cos theta, and ay of this one is equal to vector and magnitude of that vector and sine theta. So if I have to write it, the complete vector, some component ax into x hat s hat, y hat into ay into y hat. So what is ax? Ax basically a cos theta x hat and a sine theta y hat. So this is again the rule. Now you can just take it and you can take a ratio. Let us say what happens to ay by ax. So you can see just divide the take the ratio ay by ax, then this quantity would be cancelled out, and then you will just end up with tan theta, because sine theta over cos theta is tan theta. So let us say somebody has given you, let us say a vector is equal to 5i hat plus 6j hat. Then they can say that, okay, what would be the angle of this one with x-axis? Then you can just write it down. Tan theta would be 6 by 5, because it just say that the ratio would be ay over ax, the y component over the x component. So it would be theta. All right, so tan theta would be this one, and you understand that where this theta is making an angle, this theta is making with x-axis. All right, so this is how we can easily find out. So theta would become tan inverse 6 by 5. All right, so I hope this is clear to you. Now I'm going to talk about the product, and basically I'm going to in this lecture only I'm going to invest it in dot product. So let's try to find out dot product. Consider I have two vectors, a vector and b vector, and dot product is just making a dot. So dot product is also known as scalar product. All right, or maybe in quantum mechanics, if you will read, it is labeled as inner product. So dot product has a very amazing properties, that if you take two vectors and you are doing the dot product, then whatever the quantity you will get is going to be a magnitude, a real quantity. All right, two vectors, if neither of these vectors are any complex, therefore you are going to end up with some kind of real number. That's all. So because you are ending up with some scalar quantity or some inner scalar quantity, that's why it is called as scalar product or inner product or dot product. All right, so consider I'm writing a vector ax x hat, ay y hat, and az z hat. And another way I am writing it, b is equal to bx x hat, by y hat, and bz z hat. Now in order to take the dot product, what you have to interested at, always try to take x hat and x hat, because there is another property of it. A very cool property is that um suppose I can just show you from the matrix, and then we are going to talk about some cool property. Matrices x hat is basically in the three dimension written as 1010. So if I have to multiply 2x hat and x hat, what you have to do is that from the matrix multiplication, I cannot just write 100 and dot 100. This is not a rule, as you may have if you have written down. So what is x hat? I have to take a transpose of this one, this quantity transpose, and then I can multiply with this one. All right, so transpose means that the column, because it is again one column, it will become row. So 100 and then 100. So what happens is that 1 and 1, it is going to multiply by like this. So this is first column and first row, 1 plus second column, second row, second plus third column, third row, 0. Now it is coming out to be 1. So that's why, so you have got that x transpose dot x hat is going to be like this. So as I told you that this basis in 3 dimension is just like a column matrix. Therefore I have to take, in order to take a multiplication, I have to do this matrix multiplication by taking a transpose. Now since we are dealing with something called real quantities, so if I am just taking a transpose, or we can just say the complex, just transpose it, then nothing would change, everything would be made there. But in quantum mechanics, this transpose is not just only transpose, it is becoming a complex conjugate. All right, and then transpose it. So complex conjugate means that in quantum mechanics you understand that a theory is basically a complex theory, and when you what you are actually getting is that some real quantities. All right, so what you can measure is real quantity, but the theory itself is a complex quantity. So in order to get a real quantity, you have to first make a complex complex, you take a complex conjugate, and then you have to transpose it. All right, and then you can do the inner product or this dot product. Understood? And then this is actually giving you the concept of the duality and so on, that we can you must have the dual space in order to find the find the real quantity. On the other hand, when we are dealing with classical mechanics, there is nothing like dual quantity, there is nothing dual vectors, because we are actually talking about the real quantities, and real quantities is not required to be take some complex conjugate, because you can just transpose it, and over here you will get it. All right. No, so therefore I can just take a dot b vector as the surviving quantity would be just only a x hat and x hat. You may take, you may just multiply x transpose times y hat, and you will see that everything would vanish, because consider over here this is 0 and this is 1, so you can see that 0 comma 0 into 1 1 1 comma into 0 0 and 0 into 0 1, so everything would become 0 0. So if you just cross multiplication with any other quantity x hat dot y hat, x hat dot z hat, it is going to be vanishing. Therefore, the surviving quantity would be the same quantities. And I told you that x hat will give you 1. So I don't have to worry about anything. A y, b y, and a z, b z. So I have shown you that how this works. Another way of thinking that why I am getting this guy, because I can just use another definition that if I'm doing the two dot product, then what I'm just basically getting is that magnitude of a, magnitude of b, and then the angle between them, which is cos theta. All right, now this is different than the taking something of now this is the same thing, like let us say you have a vector and the b vector. All right, and if you do the dot product, then what you are first doing is that you are taking a projection of a onto b, and now since b and b becomes, taking a projection on b is basically like a vector on b is, you can just say that okay, um a dot unit vector of b hat. So this unit vector is basically giving you a and cos theta, and then there is a b hat. Now, if you just multiply with the two things over here, a dot b and b, all right, then you will get that, okay, a dot ab would be simply a vector and so on, some magnitude cos theta, b hat, and then b and so on. So you will get everything to be like this. So that is the thing. So we understand that a vector dot b vector is going to be scalar quantity. Therefore, we have the magnitude and then theta, and the whole thing is actually becoming this one. So I don't have to consider anything. I can just take over here that this is b. So ab cos theta. You can just plug it over here as well. So it is just basically taking a projection of a vector onto b, and again they have the same direction, therefore b and b would be just only b. All right, b hat, and then you will end up with this guy. All right, so now if I'm having x hat dot y hat, then you can just see that x hat and y hat, and then cos theta. What is the angle between x hat and y hat? They are mutually perpendicular to each other, so theta becomes 90 degree, so it will vanish out. Now if I am taking x hat dot x hat, then what happens is x hat and cos theta. Now since their direction is same, therefore theta becomes 0 degree, therefore the end result is always 1. So that is another way of seeing that I am using the vector definition a dot b is equal to a b and then cos theta. All right, so I have two things when I'm discussing dot product. I have explicitly two things. The one thing is a dot b is equal to ax bx, ay by plus az bz. In terms of angle, let us say a vector in 3 dimension is just only plane. So let us say I have xyz, all right, xyz, and this is some plane. Similarly, I have some plane. So what is the angle between the two planes is given by a vector, b vector, and cos theta. So another definition is this one. In order to find the angle, cos theta would become ax bx, ay by, az bz over a and b. And in order to find the angle, you can just take cos inverse and then you are good to go. All right. So if you are wondering that what is a magnitude of a is just the component squares ax ay square and simply az square. On the other hand, the magnitude of b would become bx square, by square, and bc square. So these quantities are maybe zero. If we cannot, it cannot be zero, otherwise it's not a vector. But they are obviously greater than zero. However, the multiplication of these can give you negative sign and so on. So depending on it, you can get what's your theta. All right. So I hope this is clear to you, and we understand that. And from this, we understand that what could be the angle between the two planes in three-dimensional geometry. Another interesting thing I just mentioned you earlier, that a vector dot b vector is given by a, b, and cos theta. Depending on theta is 90-degree, this is the dot product vanishes. It just simply say that if the two dot products vanishes, then these two vectors are perpendicular to each other. If a dot b is taking a maximum angle, let us say a and b, which is again going to become a positive quantity, it is becoming a maximum. All right. So I can just say that a is parallel to b. Now either it happens that a dot b and what could be the minimum of cos theta? Cos theta can be maximum 1 and then 0. And is there any way we get minus 1? Cos pi. Cos pi is minus 1? I guess so. So if cos pi is minus 1, then they are becoming antiparallel, although they are just parallel. So you can just have A and B. Correct me if I'm wrong. All right. So now it has becoming negative, but can take a maximum value of negative. So I will have this called anti-parallel. Again, it is a parallel, but two direction are opposite to each other. But obviously they are parallel. All right. Now one interesting thing is that consider I am adding two vectors, a vector and b vector. How I'm adding? Just like one vector going from over here, another vector is like this. And let us say they are making an angle some theta. So for over here, I can just take a vector and b vector, which is basically c square, is a square plus b square plus 2 into this is a, this is b, and cos theta. In another way, it is just 2 into a into b. All right. So this is how we can find the sum of two vectors just by squaring it, and we will get these two things, a square plus b square, the magnitude square and all these things, and then the inner product between two vectors with the factor of 2. All right. Similarly, I can get a minus b whole square is basically a square plus b squared minus 2a dot b, and this can be shown by like this. So a is like this, and t and negative of this one, and I still have c. So this is how we can easily find out this product. Now, as I explicitly shown you that we are going to do the multi-spatial thing, like n dimension thing, and in n dimension I have x1, x2, and so on x. These are called n tuples. So we are entering at a topology, and this must be real numbers. All right, r to the power n dimensions. So n dimension is called n dimension. Now in this case, I am going to explicitly show that I will write my basis or unit vectors like this, e3 and so forth. En. So what is basically e1? E1 is 1 comma 0 comma and so on 0. E2 is 0 comma 1 comma 0. Again, these are column matrices. En is 0 comma 0 comma and so forth. After n, this is 1. All right. So as I told you that any vector can be written as a vector is equal to a1 e1, a2 e2, a3 e3, and so forth and so on. Understood? So I can easily explicitly write it as, a1 0 0 0 0 so on, a2 0 0 0 so on in the matrix format, 0 a3 0 0 so on, and so it becoming an n cross n matrices. All right, so a vector is just a matrices. So what we can actually write it in a compact form is that a vector is basically a1 e1, a2 e2, and a3 e3 with summation sign. So I can just use summation and I can write ai ei, which is I is equal to 1 to n. All right, so this is called summation, the algebraic expression of these quantities. That if you are having this a vector, then this a vector can be expanded in terms of a basis just by doing this one. All right, so this is extremely again important, and if you when you will read general relativity, then you will realize that you are going to use summation sign, Einstein's summation, where these actually this is showing you the inner product. All right, ai and ei. So in there, in Einstein's case, I'm going to write it over here ai ei. So any indices, this is called the indices with lower indices and upper indices. So it is called the covariant and it is called contravariant. Now if you are seeing these two things, then it is automatically just say that you are actually summing over it, because in general relativity it is all depending on just the indices. All right, because we have to deal with vectors as well as the tensors. Summation is going to be a very important thing there. Therefore you have to always be sure that what is how the summation is taking place and what is the meaning of these summations. So that's why we have to be very habituated with this kind of thing, that okay, all right, if I'm having any vector, then I can always expand it in terms of basis vector, and I can use the summation sign as for an algebraic expression. All right, now similarly if you have vector in n dimensions, no problem, I can always take the magnitude of it, and it would become a1 square, a2 square, and so forth, n square. I can easily find out the angle between two planes in n dimensions by taking magnitude like this, a sorry, yeah, uh two vectors, a vector dot b vector, and then I can just take the, I will normalize it by taking the by taking the magnitude of these vectors, a vector and b vector. And similarly I have two vectors, let us say a vector and b vector, then I am expressing this a1 e1, I can just write ai ei, I is equal to 1 to n, and then another one is a sorry bi ei, I is equal to 1 to n. So what you are basically understanding, that e1 is going to be finite 1, e2 is going to be 1, because you understood previously, I just discussed. Therefore everything would become ai bi, I is equal to 1 to n, or in other words you can just write a1 b1, a2 b2, and so forth and so on, a n bn. So this is how the vector of summation or vector product is happening in n dimensions. In 3 dimensions we can find out the angles, we can find out the resultant vectors, we can find out the summations, we can find out the projection and what is the meaning of projections. All right, in the later video in lecture 3 I'm going to specifically talk about talk about the cross product, and in the cross product you will understand the determinant, inverses, and all lot of things, something involving with rotations, as well as many interesting things with related to the matrices. So again, that's why I'm saying that this is little bit devious, a little bit more rigorous and more mathematical approach to understand the vectors that you have already studied in class 11th and 12th. So I hope this lecture give you some insight to understand vectors in a different perspective. If you have gained something from this video, please like and hit the button, subscribe to my channel, and share to your friends.